Um, okay, I guess we can start. I think the coordinator will send kind of like this usual announcement about with the exam practice problems for the third exam and like the kind of like a review today or tomorrow. I will also kind of like send you the usual thing I have sent for like the first two exams probably tomorrow as well, so that you keep have that around. But anyways, like the exam is, like Wednesday of next week. So I will, but I do think I should be able to send that like tomorrow. We're done with we will be done with the material for the exam this Wednesday. So whatever we end up covering. Basically the plan is to talk a bit more today about power series. And then next time, the idea will be to discuss about, if you have a function, when is that function equal to like its Taylor series, which is like an important thing to understand. Um, Here you are. Okay, so let me just remind you some of the things I was saying last Wednesday. So the idea is that a power series, the way you should think about it is some sort of like infinite polynomial. So the way I was referring to it last time is that you take different powers of x, x to the 0, x to the 1, x squared, x cubed, x to the 4, x to the 5, for eternity, and you multiply each of those powers by a different number. You add that all together, and that is what you refer to, think of as a power series. So this is a power series. Um, there was this example we were working with on Wednesday. So like the example from last time was something like this, if I'm not mistaken. Okay. And the idea that the way you should think about a power series is that it is an expression that for some values of x will make sense, for other values of x, maybe it will make no sense. So the case that we were discussing is like last time was like, what if you take like three different values here, like x equals 0. So if you take x equals 0, then p of 0 was 0, which was perfect. If you take x equals 1, then p of 1 would be this series, which we know for different reasons that a series like this is divergent, right? Because you could compare it with like the harmonic one, like 1 over n, or so this was divergent. And then if you take x equals -1, you put -1 here, you get something like this. And a series like this was convergent because of like the alternating test, right? So like the only like the point of like this example was just to kind of like show you that depending on which values of x you choose, sometimes you would get like a finite number, and other times you don't get like a finite number, right? So for certain values of x, you know, for certain values of x, the power series would make sense. For other values of x, like the power series would not make sense. So the next step that we're going to continue discussing today is like trying to understand, you know, what else can we say? And that was what I ended up mentioning last time, which I'll write again, that usually what happens with power series is that they converge on a certain interval. That interval is determined by a radius of convergence. So I'll kind of like restart that point now and just like tell you what we were saying. Is that making sense? If I have any questions about this? Okay. Oh yeah, sorry. Oh, the thing is like when I say tailored, I do have in mind so the Taylor series is a particular type of power series, but when I refer to, and we'll talk, actually will be the focus on Wednesday. We'll go back to Taylor. But when I say Taylor, I have in mind these coefficients being like the derivative, like kind of like the k derivative of a function divided by k factorial, which was this formula I had like written last time when we talked about the Taylor polynomials and all this stuff. So when you say Taylor series, you're thinking about I start with a function that I want to approximate, right? And so like these coefficients are determined by the function. Here we're not we don't have a particular function in mind. So it's kind of like it could coincide with the Taylor series of a function, or it may not, of any, is that making sense? Um, so right, like maybe I'll make it as a remark. We'll talk about Taylor series next time, but in that case, you think of the C case as being this case derivative of the function divided by k factorial. So here we don't, for a power series, you don't need to have a specific function f of x in mind. So for a power series, you don't need to think of a particular function, to think of a particular function. Next time, for next time, we'll talk about the Taylor series, which is a specific function, which is a specific power series. That the Taylor series is a specific power series determined by a function. So the idea is like you start with a function and you find its Taylor series in a sense. Yes. Oh yeah, sure. Let me just finish writing this. Where so this is going to be like the main well, like let's put 0 here, although like you can center it somewhere else. That's not 0. I'll write the formula later. But the main difference is that again in the Taylor case, you just look at a very specific type of power series where like the coefficients have like this particular form. Now to answer your question about the divergence, like so for example, again, like that's the thing with the series, that there are like different criteria that you can use. So if you wanted to know why this is divergence, like you could do like a comparison with an integral, something like this. And then that one, like it's like an improper integral, like this P series, 1 over x, which is P equals 1. So like that would be divergent. Yeah, it's kind of like a comparison with this one. I wrote it on the previous PDF. That's why I'm like not writing it like here again. And then with -1, then it becomes alternating, because like the signs go positive, negative, depending on how you start it. And it satisfies all the conditions of like alternating series test, which was like the signs alternate and the terms are decreasing in absolute value, and then the limit of the term is 0 at infinity. So it was because like this one was convergent because of like the alternating series test. Is that making sense? So that's kind of like the thing with this power series stuff. It is kind of like very integrated with the just like regular series, because if you just plug in particular numbers for x, you just end up with an ordinary series. So all this stuff about convergence and divergence that you knew from previous, like just for series, like can be applied more or less to power series. That's kind of like the main idea. Is that making sense? Okay, so the other thing I said at the very end of the last time is that and this is kind of like one of the most important facts about like a power series. And again, I won't go into the details today, but it's part of what I mentioned on Wednesday. where it's related to the ratio test. So if you wanted to understand where this comes from, like it's kind of like you work it out through the ratio test. But the idea, which is like this is like a very important fact, is that fact is that if a let's so if you take a ratio, it's kind of like a reverse ratio if you won't remember how it went from the ratio test. But if you take the ratio of the nth term of the nth coefficient divided by the n plus one coefficient in front of the powers of x, if this number happens to be r, then the function, you know, then p of x is well defined, is convergent. Well, by well defined, I just mean that it is convergent. For any x on the interval negative r. So the way you should think about it, I think I can make that picture last time, is that you have like the number line, right? X equals 0 is safe. Like you can evaluate the power series there. And then around the number, there's kind of like a safe zone, which goes from negative r to r. And so if you choose a value of x anywhere on this interval, you know that the value of the power series is a finite number. Okay, so if you choose an x somewhere, and so p of x is finite. That's what I'm trying to say. And here p of x is finite as well. And at the endpoints is undetermined, meaning that it could be finite or not, but then you do have to check separately. So that's why it's left as an open interval. So p of negative r and p of r could be finite or not. So you have to check that could be finite or not. So that needs to be checked separately, For example, let's apply this test to the power series we were working with to see what we get. So for example, uh, let's use this on So again, here, what you have to identify is the coefficient in front of x, the power of x. So the coefficient in front of x to the k is 1/k+1. So here, or let's call it c sub n. So you have to consider, the limit as n goes to infinity of Cn divided by Cn plus 1. Okay. So this is the limit as n goes to infinity of 1/n+1 divided by 1/n+2. And again, it's kind of like the usual fraction of a fraction thing, where you can write that as a single fraction. So it just becomes n+2 divided by n+1. That is a kind of like a L'Hopital type limit if you want to do it that way. Like the important thing is like the limit, the ratio just happens to go to 1 at infinity. So this limit is just 1. So what you would say in this case is that the radius of convergence, that's how you call that. You say that the radius of convergence is 1. So, so radius of convergence is r equals 1. So that means that around 0, there's like this safe zone of like the interval -1 to 1. So any number of x that I choose on that interval, on this interval, for any number here, the power series makes sense. It's like an actual number. So if you think about it, kind of like almost like the domain, right? So the domain of the power series is is on the interval -1 to 1. And then on the endpoints, I don't know what happens. So you have to check that separately. But thankfully, we did that a couple of minutes. I wrote it like a few minutes ago, right? Like that's the first thing I almost wrote today. So at the endpoints where it's kind of more like agnostic, the test, you check separately. But we already had seen that at the endpoints, what happened? We had said for this example that P of 1, which again, just to rewrite it, was k equals 0 to infinity of 1/k+1 that diverges. And P of -1, which is k equals 0 to infinity of -1 to the k+1 that converges. And so what you would say, so that means that, as an interval, you can close it off at -1. So you would say that, for example, the interval of convergence is -1 to 1, but closed at 1. Or if you want to write it kind of more like explicitly as an inequality, that means like it's less or equal at -1 and it's strictly less, greater or equal than -1 and strictly less than 1. So another way of thinking about this is that on this interval, P of x is like a legitimate function. It's like a genuine function. You should think about it like as a regular function, like the ones that you have studied before. So So on this interval, p of x should be thought of as a function, like essentially. Yeah. Mhm. There was open at one, like when they closed at the. So this is, that is specific to this power series, right? The thing is like if you plug in one, right? If you just to zoom out, like to see like the formula for the power series, right? If you plug in x equals one, right? You have to put x equals one here, so you ended up with this series, which we had said like diverges because it was like this, comparison test with like 1/x+1, for example. But yeah, that's important. This is specific to this power series. So maybe there could be others where like the radius is one of convergence, like the radius of convergence is one, but maybe both -1 and 1 diverge or both converge, like everything can happen. There's no specific rule at the endpoints. So you really have to go through them. Is that okay? Is that making sense? Okay, no, here comes the miracle of power series. This is like the reason why power series are so great. And it's really miraculous. Because once you have okay, if you think of this as a function, once you have a function, then you want to apply calculus to it. What does it mean to apply calculus to it? To take derivatives or to take integrals, right? And the amazing thing about a power series is that you can do it in the most naive way where you just do it term by term. Okay, like because and this is like a crazy thing because if you think about it, like from calc one, you know that if you have a sum, right? If you have two functions and you add them together, the derivative of a sum is the sum of derivatives, right? And kind of like the antiderivative or like a definite integral behaves kind of like the same way, right? Um, Now, if you think of a power series as an infinite sum, right? You could think, okay, can we do the same? Like just take derivative term by term. And when you have an infinite sum, in general, you cannot do that. Like, so there are examples where that fails, which kind of makes, like, if you think about it, like, once you replace it with plus, 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 plus for eternity, like, why should that continue working? Like, like, it's maybe not so, but of course, you do have to find like an example. But if the infinite sum happens to be a power series, everything works perfectly. And so for a power series, you can kind of like take what maybe would like to call naive derivatives, naive integrals, where it's just term by term. Okay. So, and that is really miraculous. And that is really why power series are so useful because it makes taking derivatives or integration like super easy. And I'll show you some examples in a moment, which are kind of cool. But that's where like their power really comes from because the problem of differentiation or integration is like almost trivial. It's like just like especially when integration because like integrals are usually way harder than derivatives and that's why there's all these many techniques for integrals. And with a power series, it's just term by term. So like it's a great thing. So this is like the miracle of power series. If you have a power series which converges on some interval, or like by that I just means that it's well defined on some interval, right? So when I say well defined, I just mean converges. You can differentiate it and integrate it term by term. That's like the cool thing. You can like the book, I won't go into it because it's like actually like not super hard to see it, but also kind of like a detour, where you get consumed for at least 20-30 minutes. So the book kind of like goes over it. So you can read it if you're really curious. Like you have to go through the limit definition, like you kind of like just use the limit definition of the derivative, which I'll write it like here, right? Uh, what about the limit definition of a derivative? It's something like p of x plus h minus p of x divided by h, right? And then you have to compute this limit for something that looks like a power series, and then you do have to like it's not it's like super straightforward. They just leave it at that. It's not impossible to understand, but we can avoid it. We can skip it. But you can, if someone really wants to know it, like you can check like the book. Um, then you can integrate it and differentiate it term by term. Well, let's start with derivative. You can differentiate it term by term. I'll emphasize that with a different color. So what do I mean by that? So what would be the derivative? You know, let's just think about it. What would be the derivative in this case? Um, what I just mean is that you can literally kind of move the derivative inside the series, inside the sum. So you just take the derivative of one of these terms, right? But the derivative, okay, what is the derivative of, let me put it here, like, I'll actually I'll put like all the steps, just so that you see what I mean. Um, but what is the derivative of something like this? Like these CKs are thought of as constants. They're just constant terms. So like a derivative comes out of a constant comes out of a derivative, right? Um, so you're just taking the derivative of x to the k, right? Which is like just the power of x. So like the exponent rule, like just tells you that the exponent is brought down and like gets lower by one, like So is that making sense? But again, like if you think about it, it's like an incredible fact because, like, again, this goes forever. So it is like a big jump from saying that when you have 10,000 sums, you can take 10,000 individual derivatives and add them together versus infinity. Like infinity is never ending process, So it's kind of like crazy that it happens. By the way, like something that's useful usually gets written down in this case is that the way we're putting it, like the sum starts at zero. In this case, because of how the exponent rule works, when you put k equals zero here, like you get zero times whatever. So like this, like the k equals zero term is always zero, so you can kind of like drop it. And so you can start for the derivative, the sum at x k equals one. Okay, so there's nothing wrong, like, if you keep it at, There's nothing wrong if you keep it at starting at k equals zero. It's just like you always know that at k equals zero, like this is zero. So you might as well like start the sum at the first step where there's something interesting that could happen, at the first value, which is k equals one. So this is the derivative for p of x. And I'm about to show you some examples, but let me also write it for the integral first. And so I'll write it kind of like in the antiderivative form version. But if you have like an antiderivative of p of x dx, again, would that be? It would be an antiderivative. Again, like the cool thing is that kind of like for a power series, you can kind of like move the integral past the sum. Is what people call commute. Like, they like taking derivatives and integrals commutes with taking like a series. Like, it doesn't matter in which order you do them. When it's a power series, like in other cases, it does not commute. Like, you cannot just like flip the order of the operations. Yes. I mean, there could be other instances where it works, but it's just that it doesn't work in general. But in this case, like really, like, if you had to go through it, like it's just like a consequence. I mean, if you kind of write what the limit is, it works because like you have the binomial theorem, like which is kind of like a formula for what is like I don't want to put like I'll just put that here because like you would have to find something like this. Um, like when you what like you have to be careful here, but like it's something what like a simple back to that x plus h to the k minus right. So the thing is that you need like a formula for x plus h to the k, which is kind of like a generalization of x plus h squared or x plus h cubed, right? And there's like a formula for that, which is called the binomial theorem, which we can actually found. And then and that kind of like allows you to simplify like the difference, and there's some magical cancellations that happen, and it kind of like allows you to push through the calculation, and you just find, oh, it's actually the same that you can like just if you take like, the derivative term by term. But in other cases, like if the power like if the series has like a different expression, like it's just there won't be something as simple as that you can apply, that would allow you to simplify it further. But yeah, no, like there are like examples that is kind of like the sort of thing that you do like in real analysis of our or course like that, where it's like kind of like going through all the things that could go wrong in life. So like all the examples that fail, like so you're bombarded with counter examples, like things where everything breaks down. But like here, kind of we're in the setup where everything is nice. So like, like you don't worry too much. That's kind of like the idea. But is that like it's kind of like, but yeah, it's kind of like a calculation that you have to do, and you kind of like notice that it works. Um, and in this case, and also if you know complex analysis, there's another reason why it would work, but that's like a longer story. But here at least you can compute it. But if you know complex numbers, some also magical things happen there. But this is a constant. Constants come out of the integrals. So you're only integrating x to the k. The exponent rule is k plus 1 divided by k plus 1, right? So Right, and so I'm almost done here because if you think about the series, right, like it's always useful to think about what happens if you plug in k equals 0. For example, if you plug in k equals 0, you get c0, right? 0 plus 1, which is just 1. And then here you get x to the 0 plus 1. So you get x, right? Because you get x to the 1. So when k equals 0, this is starts at x. So that, you know, the lowest power of x that you see here is x. So potentially there's a constant term you could add because it's like an antiderivative, right? So you can write this as constant, like kind of like what you would call, like, what you're usually calling like a constant of integration, which is power x to the 0, right? It's like a constant times x to the 0 plus the rest of stuff you would get from the power series. And that's how you should think about this, like, this thing. I'll give, and if you ever have to take like differential equations, calc for kind of, this is like the bread and butter because like this is how you solve differential equations many times. I'll probably kind of put one example of that sort on the workshop so that you see it. But you'll see it's like a very useful thing to know. Like the fact that you know this stuff works, like it's very convenient for solving equations, and other stuff like that. And now I'm gonna about to show you some cool applications of this. Okay, so here's an example. Let me do an example of the derivative and then I'll do an example for the integral. So here's an example. Example 1. Oh, sorry, it should have been put here k factorial. So part A would be like, for example, what is the radius of like the interval of convergence? That's like what you could ask. Like, for which values of x does this make sense? Okay. So like, I'll break it into two parts. So find the interval of convergence, which is usually what you would get asked first. So that, because that's kind of like the safe zone. That's where like calculus works basically in the naive way. So find the interval of convergence. And part B, like for example, let's then you would find, and I'll show you why I would like to find this derivative, which is kind of like cool. Well, for the interval of convergence, again, you identify the coefficient in front of x to the k. Which is 1/n factorial here. And you can try to find the radius using this limit that I mentioned earlier in the class. So you take c of n divided by c of n plus 1. What is c of n? That's 1/n factorial. What is c of n plus 1? That's 1/n plus 1 factorial. Okay, and then fraction of a fraction as before. So this becomes what? It becomes the limit as n goes to infinity of n plus 1 factorial divided by n factorial. Like the factorial is really important in this type of problems, so like again, like the only real property you have to remember is that n plus 1 factorial is n plus 1 times the previous factorial, like this recursive definition. So this is n plus 1 times n factorial. And that's great because you were dividing by n factorial there, right? So you get the limit as n goes to infinity of n plus 1, right? Well, which just happens to be infinity, right? Okay. Which means everywhere is safe in this for this particular expression. So any number, any value of x that you plug in, you would get a finite answer. So like the safe zone is like the entire number line, like the real numbers. So there are no endpoints here to worry about because the endpoints are like at infinity, like it covers. There's no number that doesn't get covered here. So like the interval of convergence is everywhere. So interval convergence. There are two ways to say that. It would be, you can write like R, which is like a nice fancy way of referring to like the number line, or like negative infinity to infinity, like whatever you prefer. Okay, and is that making sense? So that's part A. Where does this expression make sense? So just to summarize, so what I'm saying is that this is finite. So this is finite for any x. Doesn't matter what you plug in. Okay, and then part B was asking you to find the derivative here, right?
The the factorial function just like grows so fast, it's just all going to.
I mean, that makes, right, like, basically, yeah, right, that if you pick a finite x, right, different powers of x don't grow as fast as just like the, like the k factorial. So that kind of like the denominator is growing so fast that it forces like the convergence, like the series to occur. But like sometimes, but also x to the k grows fast. So like, like that's why the calculation is kind of like important, just to kind of like do like check that the numbers work. But yeah, like the factorial is like a very fast, like almost like like most of like things like factorial is kind of like so big for there are like all these approximations for n factorial, um which is called like the Stirling formula and other things. But it is like, yeah, it's really really big. So like, like, so yeah, like that's kind of what's going on secretly. The factorial kind of like makes everything go to like converge, because each growth is so fast. Okay, now let's look at this one. So again, the cool thing about power series is that you can do the naive derivative. Naive derivative is just like, this is a constant, so take the derivative of x to the k, as we were saying, bring the k down. So you just end up getting the series from k equals 0 to infinity of k x to the k divided by k factorial, right? Is that okay? Now, that is the answer in a sense, but I do want to simplify it because something cool happens with this one. So, what is k factorial again? That's k times k minus one. Well, first, we can do the thing that I mentioned before, where like this series, if you put k equals 0, that kills everything, right? So you might as well start the series at 1. Yeah. Oh, yeah, yeah. Thank you. Yeah, yeah. Good catch. Yeah. No, you are supposed to. Yeah, I just forgot, but glad that you caught it. Perfect. Now we're good. So, as I was saying, like the k equals 0 doesn't really contribute in any of these cases, because when you bring down the k, that kills whatever else you had. So we can start the series at k equals 1. So I'll put in color that, just to emphasize, the only thing I changed here is that I put k equals 1, right? And then if, again, in a sense, this is the answer, but you can simplify this further, because k factorial is k times k minus 1 factorial, right? So this becomes like the series from k equals 1 to infinity of k x to the k minus 1 divided by k times k minus 1 factorial. Is that yeah, sorry. Oh, right, because it's just like a small simplification, because like the sum starts at 0, right? But if you take k equals 0 here, you're getting a 0 in the numerator, right? Because like if you replace k with 0, you get 0 times whatever. So like that, So what I'm trying to say is that this is the same as like, 0 plus the sum from 1 to infinity of k x to the k minus 1 over k factorial. Because at k equals 0, like everything gets killed off by this exponent that was brought down, if that makes sense. It just, the thing is, like, this is useful in the next step, because like if I use this formula that k factorial is k times k minus 1 factorial, like you don't want a negative number here, because I didn't tell you ever like what is like negative 1 factorial or negative 2. There are ways to kind of try to define that, but we're not getting into that. Oh no, it's that okay? Here it was just because I was asking, like, asking you to do it, but something kind of interesting happens once we fully simplify this, which is what I'm trying to get at, but yeah, it's kind of like, just test that, like this very, like, apply property that you can differentiate term by term. But in this particular form expression, there's something cool that happens if you kind of, we're almost there where we are fully simplified, but you'll see that something interesting does occur here. But yeah, like, like a typical problem, kind of like the typical problem of these power series things will be find the interval of convergence and then differentiate or integrate or do something like that just to test that, also that you can just do it term by term, if you know what I mean. Okay, well, now cool, because you can get rid of that case, right? Uh, Okay, and again, that's kind of like a simplification. What's kind of like interesting here, is that, really in this sum, like you always have k minus one, k minus one, everything depends on k minus one. So I think that you can do, it's kind of like an analogous thing to a U sub, which is just like, kind of like do a substitution, because like that way you don't have to see k minus one every single time. So instead of calling it U, I'll just call it L, just continuing with the alphabet, but it's kind of like, think about it as a U sub type thing. So I'll call like, it's kind of like a U sub, but for the index, not for like that variable. So I'll just call L k minus one. So what happens if you do that? Then you get x to the L, right? You get x to the L because now L is k minus one. Divided by k minus one factorial, but k minus one factorial becomes L factorial, right? So the only thing that changes here, I mean, we're kind of like doing like a substitution of sorts. So the bounds, right, like the sum was for k. If you want to write everything in terms of L, you have to rewrite the bounds for in terms of L, right? So instead of like saying it before the sum started at k equals one, now I want to say something about where the sum starts in terms of L, right? So what should you put here? Where should the sum starts in terms of L? Right, zero, because when k is one, I'll write it in a moment, but when k is one, you get one minus one, which is zero. So notice, right, notice. So this is kind of like, when you do like a U sub in a definite integral that you have to change the bounds for the definite integral, I'm kind of like doing that part here. Well, I'll put it as one minus one just to make it more clear that that's what I'm saying. And infinity, like if you wanted to think about it, when k equals infinity, what is L? It's infinity minus one, which is infinity, right? Like it only affects really like the lower bound, like where the sum starts. Like so. Now the thing is this recognizable? What is this? It is exactly the same sum. Like it doesn't matter what name you give to the index, right? Like it's kind of like a dummy variable. What you call, I sometimes I call this k. I have called it sometimes n. I happen to call it L now, like but it is the same sum, right? So this is actually p of x again. So, if you look at it, it has exactly the same format. It's just like I use like a different dummy. That's why they're called like dummy variables or dummy indices, because like it doesn't matter what letter you identify them with. So what we just found is that P of x is a power series that equals its derivative, right? But you know a function that equals its own derivative, that's the exponential function, right? So essentially P of x I'll tell you that next time, but P of x is a power series representation of the x e to the x. So, and that's actually, okay, if you ever take differential equations, that's what you do, because what you have in differential equations is kind of like a uniqueness theorem, which says, basically, this is called like a differential equation because it's like an equation involving derivatives, and there's like a uniqueness theorem that says that basically, if you specify the initial value, which is kind of like the value at zero, there's only a unique solution to this system. So if you just found the functions that equals its derivative, it must agree with the exponential. So a more elegant approach is you define the exponential as a power series, and then you can just prove that it's almost like trivial that it is own derivative, like the problem of showing that the exponential e to the x prime equals e to the x, like it becomes collapses because there's nothing to show. So like that's kind of like the most elegant way to define e to the x as a power series, and then you're done. But then you have to prove like other properties that you know of e to the x, obviously, but but again, I'll kind of tell this in more detail next time, but so what will happen next time? And we'll see that this is just really like e to the x, which I had like advertised before, but uh, because like actually the exponential is basically the only function that equals its own derivative. Like that's the main idea about the exponential, except for something dumb like multiplying it by a number or something like that. Like like up to like some constants, it is like the only function with the property that its derivative is itself. Like like it's like a nice thing that follow, like another example for example. Okay, now let me give you. We have only 20 minutes. I'll give you an example with integration. So here's an integral example. So now another one. So let's say that you consider. Let's find the interval of convergence just as before. Well, actually, let me I'll put it like this already.
Start thinking that that's after.
No, because that's kind of like the thing that's always, but like if you look at the radio formula in terms of like the limit, it is a limit, right? So it doesn't matter what the initial coefficients are. That's the thing with like, the interval convergence just means what numbers can I plug in where the corresponding series would be finite. And I think we have discussed it before. on a series, you could throw out the first trillion terms. Like that's like the same thing with series. Like it doesn't matter how many terms you forget. It only matters at infinity what it's trying to do, because that's what controls whether the sum goes to zero, like converges to some finite number or not. So yeah, strictly speaking, it's just like the convention in the power series. Like the convention is to start at zero because you want to think kind of like constant term, constant plus linear term, constant plus linear plus quadratic, constant plus linear plus quadratic plus cubic. So you want to think about it as kind of as a full limit of polynomials. But if for convergence, you could have started at degree 10 trillion, and it doesn't matter, like, the interval of convergence does not depend ever on what the first few terms, like, you can throw off as many terms as you want. Does that make sense?
Yeah.
Okay, and then I'll integrate this one. Okay, so this one is, okay, let's start with the interval of convergence. We can use the formula for the radius of convergence. So here's Cn, it's just like, again, it's always the coefficient in front of x to the k. So Cn in this case is -1 to the k. And for the radius, we have to look at the limit as n goes to infinity of the Cn's in absolute value, right? So that's why I put like the negative ones, because they're more interesting that way. So okay, there's not much to compute here because, absolute value turns everything into positive, right? This is always -1 or 1 depending on whether n is even or not, but absolute value just turns everything into ones. So you just get 1/1, which is 1, right? I mean, it doesn't depend on n at all, right? It's just 1/1, which is just 1. Right? Now, what does that mean? It means that the safe zone is the interval -1 to 1, right? So this is, the safe zone is from -1 to 1. Convergence happens everywhere in here. What happens at the endpoints for this case? So what is P? Oops. Um, what is P of 1? That would be the series of -1 to the k times 1 to the k, right? Which is the series of -1 to the k. And anyone remembers what happens? Does that converge or diverge? What do you think? It diverges. So one way to think about it is like if you just plug in some values, you get 1, -1, 1, -1, not 1, -1. Like it always oscillates the sums, the terms that you're adding between 1 and -1. So it doesn't satisfy the nth term test because at infinity, this just doesn't go to 0, right? So diverges, right? Because limit as n goes to infinity from -1 to the n is not 0. Is that making sense? So it always is oscillating between -1 and 1. So the partial sums do not converge to a specific number. And what happens at -1 is you'll see something similar. Oh, isn't it even worse? Because now there's a bunch of ones, right? Because it's -1 to the 2k, and that becomes ones, like it's even worse. Perfect. So this one is even more clearly divergent because you're just adding a bunch of ones. So divergent. Okay, so what does that mean? That means, so summarizing, this expression, right? Convergence, right, on the open interval -1, 1. Now, I claim that you actually know what this is already, a more simplified version of that, if we just change the names a little bit. Because, and here comes okay, so now notice that what is P of X? P of X, another way of writing this is as -x to the K, right? Let me call R -x. So call R -x. So this becomes a series of K equals 0 to infinity of R to the K. What is, does it remember? Geometric series, perfect. Which converges when in absolute value is less than 1. This converges when in absolute value is less than 1. It cannot be a coincidence because it's literally the same geometric series. It's just got a mental trick because before you thought about this as a fixed number, now I'm thinking about it as a variable, right? And if you remember, there was like an actual formula for the value of the geometric series. Usually in class, I started it at 1. If you started at 0, it's even simpler. It's 1 over 1 minus r. Like if you started at 0, so it's even nicer. So then if you go back to, if you rewrite this, so that means that like this series, the value for this series, okay, what is negative r? Negative r is x. So it becomes 1 plus x. But I mean, it's like a very clever thing. Like, like the geometric series is so important here because it's kind of like hidden, like many times you don't think you have it and then you just call R something and then it pops out. So I'll do another example of like that next time, but I'll now answer the second part, which is let's integrate this with respect to X. So now integrate for part B, and I'm almost done. So if you integrate, that means that the integral of this series should be the same as the integral of, with respect to x, of 1 over 1 plus x. Okay, but what is this? Integrate each term, right? So it's x to the k plus 1 over k plus 1. But what is this integral? What do you integrate this? What is the integral of 1 over 1 plus x? If there were no x, if there were no 1, right, this is ln of 1 plus x, right? Because it's just like a u sub, like, so now you just found a power series for the lateral log of 1 plus x. It is 1 plus x because it's centered at 0, and you remember ln is undefined at 0, so you needed like an extra shift for it to kind of work nice. So here you don't even need absolute values because x is always between -1 and 1, and if x is always between -1 and 1, then like this is always positive. So like the ln is well defined. There you go. Like that would be the Taylor. Actually, this would be the Taylor series for ln of 1 plus x. Like so next time the goal for next time is kind of like, I'll tell you if you start with a function, when will it agree with its Taylor series? But I was trying to show you without telling you ahead of time that you can already find some Taylor series by very clever tricks like this. Of course, you have to be strategic about it. But it's like a cool example, because that's kind of like how many of these functions that you know from top one, like actually appear. Sometimes it is easier to understand them as a power series because that way it's better to know, like that way you can know their properties more, like of their derivatives or integrals more easily. Okay, I think that's a good place to end. So let's end here and we'll continue talking about all this stuff on Wednesday. Let me just pause the recording. Let's see. Yes. Oh, the thing is like any factorial, remember like when it's a factorial, like for example, what is 4 factorial? One times 2 times 3 times 4. So it's always any factorial, is the previous factorial times the ultimate like last number. If that makes sense. Yeah, yeah. Oh, the thing is like, if you kind of notice, I can it was like secretly a geometric series, right? I do get this formula from the geometric series. And then once you have an equation, you can take derivatives on both sides of the equation or integrate both sides of the equation. So I literally just put like separate integrals. Yeah, so it's otherwise I wouldn't be able to identify this with the natural log. Correct, yeah. Let me see. Let me stop. Wait. Let me stop like the meeting, and then